Okay, this is a video, YouTube about analyzing a mass M hanging from two equal length strings. And so um, these black lines going from the mass up here, the first part of which are obscured by my tension vectors, are holding the mass. The mass therefore is acted on by three forces, an mg downwards, straight downwards, and then two diametrically opposed tension vectors, not diametrically opposed, but one acting up to the right and one acting up to the left, and they're both the same length, and they're both pointing along the string. The string is angled theta degrees with respect to the horizontal, and theta is the same for both of these because the length of the string on either side is the same. And so here's my coordinate system, x and y, and to simplify the problem now, I'm going to take force components of the t vector, one pointing upwards to the left and the other one pointing upwards to the right. Because if I do that, all my forces are going to be either in the x and the y direction, and then I can do Newton number twos, first of all in the x direction and second of all in the y direction. So towards that end, I'm going to take the tension vector that goes upward and to the left, and I'm going to break it into an upwards t sine theta component and a horizontal minus t cosine theta component. And I am going to take the t vector that goes upwards and to the right, that represents the tension in the rightward string, and break that into a t cosine theta plus t cosine theta in the horizontal direction and a t sine theta in the vertical direction. And since m is in equilibrium, all of these forces have to add to 0, and all of the accelerations, both a sub x and a sub y, are 0. And so that now leads to these two Newton number 2 equations. Newton number 2 in the x direction, basically, since a sub x is equal to 0, t cosine theta minus t cosine theta is equal to 0. And you can see that that happens because the length of the strings are the same. Newton number 2 in the y direction, again, a sub y is equal to 0, and so that means that the sum of these two force vectors has to cancel this. In other words, 2t sine theta minus mg is equal to 0. Now go back and make sure you understand why this is t sine theta and this is t cosine theta. Well, look back at earlier material that we've covered if necessary. So the most useful piece of what we've done here is going to be the y equation, Newton number 2 in the y equation. The x equation cancellation is automatic, but in the y equation it puts a condition on the tension. And so taking this equation and then reducing it to 2t sine theta is equal to mg, and then solving for t in this last step gives me tension is equal to mg divided by 2 sine theta. And so this is the relationship between the tension in the string, the weight of the this mass, and the angle. And then so first of all, there's some simple things here. Tension is proportional to weight. So if you double the weight, you are going to double the tension. And so that's probably intuitively clear. But there's an interesting thing going on with the angle here. As you should know, sine is smaller when the angle is smaller. And that means that the tension will increase as theta gets closer to 0. And the meaning of theta becoming closer to 0 means that the two sections of string are becoming more nearly horizontal. And so to show you how that works, let's put some numbers in here. Let's say that I had 1 kg for m, and that theta was equal to 45 degrees. And so in that case, this string would be angled down as I'm showing with the cursor at a 45-degree angle. That's a fairly large deviation from a horizontal string. And if we put the numbers in here, so basically I'm going to put 1 in here. I'm going to use easy numbers and put 10 in for g, and then I'm going to put 45 degrees in for theta. The tension in each string is 7.1 newtons. Now, on the other hand, if I make theta equals 1 degree, well, that would mean that the two sections of string are nearly horizontal. In that case, I have the same numerator, 1 kg times 10 meters per second. In other words, the weight is the numerator. But in the denominator, I have 2 times the sine of 1 degree. 1 degree is pretty small. And so what you get for the tension in each string is a whopping 206.5 newtons. It's quite a bit bigger than the 10 newtons, which represents the mass. And so let me pose a question. Can theta ever be equal to 0? In other words, can a person, Arnold Schwarzenegger, for example, hold each one of these in his hands and pull apart with a force necessary to make theta equal to 0? I'll let you think about that.